The reason of analogies in physics, part 3. Summary of the previous lecture. The fundamental equation of a physical theory is an equation that links the source with the potential of the field. Dealing with a physical theory, we have two viewpoints also to descriptions. The system or material or Lagrangian description, the spatial or field or Eulerian description. In the system description, the physical laws are expressed by ordinary differential equation, which contain the time derivatives, while in the spatial description they are expressed by partial differential equations. The global variable and field variable. The global variable in space are those variables that are not densities of other variables. This class includes the integral variables. In the spatial description, each global variable has a natural association with one of the four space elements, that is points, lines, surfaces, and volumes. This suggests the introduction of a cell complex in addition to a coordinate system. The birth of cell complexes. The role of cell complexes in the spatial description. The differential formulation of physics, making use of the point functions, needs a coordinate system in the space region where a field is defined. This is needed because to every space point we must associate its coordinates, that is, numbers. But if we use global variables instead of the field functions, that are point functions, we must consider not only points, but also volumes, surface, lines. This fact invites us to introduce a cell complex in order to have a reference structure which involves not only points but also volumes, faces and edges. The balance equation makes reference to a cell. Thus, when writing a balance, for example the balance of a mass, we are forced to consider a volume and to say that in every time interval the decrease in mass inside the volume is equal to the mass output from the volume at the same time interval. This is the balance of mass. The use of differential formulation obliges us to consider infinitesimal parallel pipes delimited by coordinate surfaces. Nothing prevents us from considering them as members of a cell complexes. Let's remark that a balance is valid for regions of whatever shape and of whatever extension, not only of infinitesimal extension. A paradigm, the heat conduction. Let's consider a linear sequence of rooms. Let's now suppose that the side walls, lateral side walls, the ceiling and the floor are insulated. In this way, heat can only cross the separating walls, the walls that separate the rooms. In each room there is a radiator. The heat crosses the walls that separate each room from its adjacent. Since the temperature inside the room is not strictly uniform, we must recourse to a mean value. We take the temperature in the centroid of each room as representative of the average values. And we give much importance to this choice. By doing this, every centroid becomes a natural candidate to be the complementary element of the volume. Then we have the volume, in this case a room, and its centroids, called these complementary elements. Here we have the table of the complementary of space elements. For a point, it is a volume. The points are dimension 0, the volume has dimension 3. For a line that is one-dimensional, it is a surface that has 2 dimensions. For a surface, it is a line, and for a volume, it is a point. For example, here you have a surface. This is a complementary element, this line. Let's consider the centroid of each room. We observe that the heat current, joule times second, that is watt, that crosses a wall depends on the temperature difference between the centroids of the 2 adjacent rooms. This suggests to consider the straight line connecting the centroids as the complementary geometrical object to the surface representing the walls. Here. The plane surface and the orthogonal straight line passing from its center can be called complementary elements. Let's denote by capital P the heat generation rate in watt, the rate of the heat emitted by the radiator. By phi, the heat current, also in watt. By capital T, the temperature in degree Kelvin. By G, the temperature difference, also in degree Kelvin. Then we have 4 variables. The global variables here considered are temperature that is associated with points, the temperature difference that is associated with lines, the lines that connect the points, the heat current that is associated with the surface, the walls that separate the room, and the heat generation rate emitted by the radiator, that is a physical variable associated with the whole volume, with the room. Now, complementary or dual. In the terminology of cell complexes, a branch of algebraic topology, instead of the proper term complementary, it is custom to use the misnomer dual. You can see the book of Franz Algebraic Topology for this criticism. This use conflicts with the notion of duality in algebra and geometry. Nevertheless, the term dual is also commonly used in computational physics, where the terms like vonoid dual, barycentric dual, and similar are commonly used. Therefore, by adhering to the common practice, instead of the term complementary elements, we will talk about dual elements. Hence, these, the surface and the corresponding line segments that cross the surface, will be called the dual elements, and also the volume and the centroids will be called dual elements. A classification diagram for space elements. The introduction of a cell complex leads in a natural way to construct a classification diagram for the 4 space elements The starting point is to dispose the four space elements in a vertical column in order of increasing dimensionalities. So for the points in the first box, the upper box, and the point is represented by the vertices of a cell complex. The lines in the second boxes and these lines are represented by the edges of the complex. The surfaces in the third box, and these are represented by the faces of the cell complex, and the volume by the cell themselves. In two dimensions, a cell complex can be obtained by a Cartesian system. In this complex we have two families of lines, the horizontal and the vertical ones, while there is only one family of points and one family of cells. Here, one family of points, two families of lines, horizontal and vertical lines, and one family of cells that here are surface elements. We will call primal this complex and denote each of its elements by putting a bar over the letter. Here we have one point, two family of lines, one family of surface or of two-dimensional cells. The space element can be classified as shown in the diagram on the right. The factor considering the temperature of the centroid of a room as representative of the temperature of the whole room suggests to consider the centroids of a cell complex as vertices of a second cell complex here, connecting the centroids with the lines and considering also the faces. The two cell complexes constitute a pair of cell complexes in duality. We are free to call one complex the primal and the other the dual. In the case of heat conduction, it is convenient to call primal the green complex and dual the red one, the one formed by rooms. Hence, primal does not mean that it's the first that has been constructed. It is just a conventional name. One is called primal, another is called dual. Which one can be decided every time, performing the most convenient choice for the problem at end. The complex, the real complex here is called the dual and the green one, primal. As we just said, starting with the first complex, one can construct a second cell complex by considering the centers of the cells as vertices of a second complex here. Also, for the dual, you have one family of points, two families of lines, the horizontal and the vertical ones, and one family of surface. We put a tilde over the letter to mean that these are the cells of different dimensions, zero-dimensional cells, one-dimensional cells, these are segments, two-dimensional cells, are the elements of the dual cell complex. Let's remark that the elements of the two cell complexes correspond one to another in inverse order. With every cell here, in the green, of the primal complex, there is a corresponding vertex here of the dual, and vice versa. To every cell of the dual complex in red, there is a vertex of the primal complex. For this reason, the classification diagram of the dual elements here on the right side is inverted with respect to the one of the primal elements. As you see, points, lines, surface, and this is inconstant to the point, lines, and surface of the primal complex. In three dimensions, a Cartesian cell complex is made of cubes, and its dual complex at the vertices as the centers of the cells here. If you connect the different centers, you obtain one cell of the dual complex. Of course, instead of cubes, one can consider parallel pipes and sides of different lengths. Let's consider a three-dimensional cell complex formed by means of a Cartesian coordinate system. We have the four space elements that are the vertices, the edges, the faces, and the cells themselves. These are representative of points, lines, surfaces, and volumes. Now, where we have one family of points, and we put here one P bar. Three family of lines, or if you want, three family of edges, and we put here 3 L bar. Three families of surface, three kind of surfaces. And then we put here 3 S bar. One family only of volume, 1 V bar. We have one family of points of the dual complex, but three families of lines or of edges according to the three directions of the space. Three family of surfaces that are the three families of faces formed by the coordinate surfaces, and one family of volumes, these are the dual cells. The number 1331 denotes the number of families of elements. The coefficients denotes the families of elements in 2, 3, and 4 dimensions. Here in one dimension we have one family of points and one family of lines. We are working in one dimension along a straight line. This is a classification diagram for the space elements, or if you want, for the cell elements in 2 dimensions. This is the classification diagram for the space elements in 3 dimensions. And you can see that the coefficients 1, 3, 3, 1 are exactly the coefficients of the Pascal triangle. For example, if you consider space-time as is essential in relativity, you have 4 coordinates, the 3 space coordinates and also the time. And in this case, the space-time elements are one family of points called events, 4 families of lines, 6 families of surface, 4 families of volumes, and 1 family of hypervolume. The 2 types of orientation of space elements. Every space element can be oriented. There are 2 types of orientation: the inner, also say interior orientation, and the outer or exterior orientation. The notion of orientation of a geometrical object is not commonly treated in physics books. So the volume of a space region, that is the extension of the volume understood as a space region, can be endowed with inner or outer orientation, and this rarely appears in book on physics. Let's remark that unhappily, while a line has a length, we speak of the length of a line, of the area of a surface, for a volume there is not distinction. A volume has as extension also a volume. The same term denotes both a space region, a three-dimensional region, and its extension. This is an unfortunate circumstance that in the history of geometry, a term different from the volume to denote the space region has been introduced and has never been introduced to denote the extension. An important point must be stressed. When we perform the density of some physical variable, say the line density, the surface density, the volume density, we must divide the physical variable for the extension of the space element, but without considering its orientation. That is, we must divide for the absolute value of the extension. This is what is done in physics for many centuries. Nevertheless, you can find some authors that consider mass density, pressure, and other variables as pseudo-scalars. You can see this by searching in the internet with the words pseudo-scalar pressure. That is a wrong expression. The sign of physical variables. Every physical variable is endowed with a sign. This means that global variables are associated not only with space elements, but with oriented space elements. The sign of a global variable depends on the orientation of the space element to which it is associated. It follows that the physical variables change sign when we reverse the orientation of the associated space elements. And since there are two types of orientation, the inner and the outer one, that we present in a moment, some variables change sign when we reverse the inner orientation, while others change sign when we reverse the outer orientation. Well, what is the inner orientation? Let's start with a surface. The inner orientation of a surface is a compatible inner orientation of its bounding edges. What means? Means that you choose on the boundary of the surface one arrow and you propagate this arrow along the whole boundary. This indicates a direction of rotation around the surface. And this means compatible. Compatible means that two adjacent elements like this edge and that edge induce an opposite orientation of the common boundary. Then the opposite orientation means that while this arrow is incoming at the vertex, this is outcoming at the vertex. This is the opposite inner orientation. In the case of a cube, or of a volume in general, you must decide on the boundary of the cube to choose an orientation, an inner orientation in this case, fixing a direction of rotation, in this case anti-clockwise, and you must propagate this anti-clockwise orientation to all faces of the cube. You might turn the cube and to the face that is in front of you, you choose the inner orientation anti-clockwise. The opposite orientation is this one, with all faces oriented in clockwise direction. The inner orientation of a line, of course, is a direction that goes from one extreme to another, and the inner orientation of a point is this. We consider positive all lines that are oriented towards the points, or if you want, the arrows that are incoming to the point. Then we consider the point as a sink, or vice versa as a source. What is curious is that in the book of algebraic topology, many topologists say that it makes no sense to give an orientation to a point. And this is due to the fact that that considers the extension as fundamental. And since the point has not extension, one say the point is not orientable. But if you consider the network theory, for example, in circuit theory, to write one of the Kirchhoff law, you must decide that the currents that are incoming to a node must be considered all positive or all negatives. In doing this, you have oriented the nodes, and their nodes may be oriented as a sink or as a source. We denote the inner orientation of the space element putting a bar of the letter. We want to show that points are usually oriented as things, even if this is never explicitly stated. Let's consider the graph of a function. What is the increment of the function? It is defined at the value of the function in the second point minus the value of the function at the first point. Now, where this minus sign arises and the plus sign here arises, you can consider the points oriented as sinks. Then the arrows that are incoming to each point must be considered as positive. And, of course, the line segment has the inner orientation of the Cartesian axis, x. Then you see that this arrow is in concordance with this arrow. Then you have a incidence number that is +1. On the contrary, the same arrow is in discordance with the arrow of the point. And then we have an incidence number that is -1. In fact, when we define the increment of a function, the sign we use can be considered as the incidence numbers between the orientation of the interval and the orientation of its bounding points. In fact, these are the -1 here and the +1 here. This is universally defined the increment of a function. Hence, in this definition, there is an implicit recourse to the incidence numbers of the inner orientation of points and also of segments. The same, of course, is in space. For example, the increment of temperature is along a line segment oriented here, is a difference between the temperature at the final point minus the temperature as an initial point. But these plus and minus signs are exactly the incidence numbers between the orientation of the segment and the inner orientation of the point. Outer orientation. The outer orientation of a volume means that the arrows crosses the boundary, the faces, They may be oriented outward or inward, and both the case are considered as giving an outer orientation. Here is the most common one in physics, but in the past centuries the arrows was taken positive inside, as the time of Maxwell, for example, or the book of Thomson and Tite. You can see that the arrow was taken positive when incoming. Independently of this, we speak of outer orientation. The outer orientation of a surface may be denoted by an arrow that crosses the surface, or also by the choice of the two sides of the surface. One is the rear, another is the front, like the page of a book. Outer orientation of a line. This is strange, is not commonly considered, but it is considered when dealing with polarized light. You have the light beam and you consider left-handed or right-handed polarized. When the plane of polarization rotates, going from one extreme to the other extreme in the anti-clockwise or in clockwise sense. Then the outer orientation of line, it is a direction of rotation around the line. This is very unusual. The outer orientation of a point. A point is said to be equipped with an outer orientation when we consider all the lines that are incidents the point as endowed with an outer orientation. And of course, if you choose an outer orientation for one segment, you must propagate turning the segment to all possible other segments. These points have two opposite outer orientations. And the outer orientation of a point is denoted by tilde. As you remember, we have used the bar to denote the element of the primal complex, the one put in green, and the tilde for the elements of the dual complex. Then we have implicitly assumed that the element of the primal complex will be endowed with inner orientation, while the elements, the space elements of the dual complex, will be implicitly endowed with outer orientation, as we shall explain later. Here we summarize the different orientation. For a line, this is a traditional orientation. This is the outer orientation of a surface, an arrow that crosses the surface, or distinction between the rear and the front. This is an inner orientation of a surface. Look here at the bar, and a direction of rotation around the surface. This is a direction of orientation around the line, and this is an outer orientation of a line. This is an inner orientation of volumes, and this is an outer orientation of volumes. Here you have the inner orientation of a point, and here the outer orientation of points. As you see, we have four elements, points, line, surface, elements. But since every element can be endowed with inner or outer orientation, the number of distinct elements is doubled. They are 8. Then we can say a point with inner orientation or a point with outer orientation. A line with inner orientation or a line with outer orientation. The elements, oriented elements, becomes 8. But we have also two possible direction of the orientation. The same line, for example, may have one or the opposite orientation. Hence we have doubled the number of space elements. We have 16 distinct space elements. Well, it is beautiful, as we shall explain in the next lecture, the fact that for every physical variable has a link, is related, is associated with one of these four space elements endowed with the inner or outer orientation, and then we have essentially 8 possible classes, elements, physical quantities, each one with this double sign. A matter of notation. We distinguish space elements from their extension by using boldface character. For example, a point with inner or outer orientation that belongs to the dual complex, if it has outer orientation, to the primal complex, if it has an inner orientation. And the line denoted with a boldface character, while the length in meters is simply denoted by capital L. A surface is denoted by a boldface character or with a bar or a tilde, but its extension, called area, psi in meter square, is simply denoted by capital A. A volume in boldface with a bar or with a tilde, but its extension is denoted simply by V, not in boldface. Psi, the unit is meter cube. Inner, outer orientation of a cell complex. Primal and dual complex in 2 dimensions, we have already said that we may construct a cell complex, in this case by a Cartesian coordinate system, and these are its elements. Now, each element may be endowed with an inner orientation, hence each node, each vertex, is considered as a sink. Each surface, this is a 2-dimensional cell, is endowed with an inner orientation. For example, we choose the counterclockwise orientation of the cell. And the edges that 1-dimensional cells are all endowed with an inner orientation, with an arrow that go from left to right in this case, and the vertical ones, and arrows that go from bottom to top. All points are oriented as sinks and so on. Now, automatically, when we introduce the dual complex, all the elements of the dual complex, the red one, will be endowed with an outer orientation that is induced by the inner orientation of the primal complex. Look here. You have, for example, this is a 1-dimensional cell of the primal complex that has an inner orientation. The same inner orientation becomes an outer orientation for this dual element. The same is for the segments, the edges of the primal complex, horizontal edges, and the vertical edges of the dual complex. The same is for the point. You have every primal cell endowed with an inner orientation. But at the same time, every dual element that is a node, a vertex, has an outer orientation because it has a direction of rotation around it. And if you consider a dual cell, since every element of the primal element here is that is a node, is endowed is considered as a sink, automatically these arrows pointing inward can be considered as orientation induced on the dual cell. We put here this. Now we have a remark about the outer orientation. This is a point of the dual cell that has an outer orientation when we have a direction of rotation around it. These are the elements of the dual cell that cross the edges. In the case of a dual cell, since here we have a sink, we have the arrows that are incoming. But to respect the traditional convention according to which a two-dimensional cell in space, in the plane, must be endowed with the outwarding arrow, or outwarding normals, these arrows must be changed, and then instead of being oriented inward, they must be oriented outward in order to respect the convention. Hence we can say that the orientation of all elements of the primal complex induce an orientation to all elements of the dual one, but in particular for what concerns the orientation of a two-dimensional cell, we must change the induced orientation into its opposite in order to agree with the traditional convention in physics. Let's consider a three-dimensional complex formed by a Cartesian coordinate system. We have four space elements that are the vertices, edges. We have in green the first, the primal complex, and all its elements are endowed with an orientation. The edges are reoriented according with the Cartesian axis. Every face is oriented with, in this case, with counterclockwise orientation. Now, let's observe the dual complex. Since there is an edge of the dual complex that crosses the face of the primal complex, we see that the inner orientation of the face becomes an outer orientation, look here, this, for the dual edge. And what is the inner orientation here of the primal edge, of the edge of the primal complex? Becomes an arrow that crosses the surface, the face of the dual cells. Hence denotes an outer orientation of the dual complex. Here we have, once more, one family of points, three family of lines, three family of surface, one family of points, three family drawing that is accompanying the classification diagram of the space elements. Then we can conclude that the inner orientation of a primal complex induces an outer orientation to all elements of the dual complex. This, in conclusion, is a classification diagram for the space element in three dimensions: outer orientation, inner orientation, primal complex, dual complex. These are the drawing of the two complexes. Now let's examine in particular the primal and dual complex in one dimension. In this case, we must consider only an axis and a set of points of this axis. These are considered as vertices of a complex that is formed by they and also by the line segments connecting two points. The whole set of points and lines form a primal complex. Now, in order to construct a dual complex, we take the midpoints of these segments, and these will be called dual points, also complementary points. And the dual segments here in red are L1, L tilde 1, L tilde 2, and so on. Now, we decide to give an inner orientation. This is a diagram corresponding to the one-dimensional cell complex. Now we fix an arrow to all line segments, that is, these are arrows in the direction of the axis. After we fix an orientation, an inner orientation to all points of the primal complex. All points are endowed with an orientation as sinks. Well, the inner orientation here of the primal segments is transported to the dual points. They assume the same inner orientation of the corresponding segments of the primal cell. Now, the outer orientation here, look here to this switch, is obtained attributing the inner orientation of the primal point, but into the opposite in order to maintain here the arrows going outward. And this is a convention that is valid, as we shall see in next lectures, also, for example, for acceleration. Acceleration is the difference between the velocity at the second instant minus the velocity at the first instant divided by the duration of the time interval. Then this choice of the arrows pointing towards the line, this is a line segment, is used commonly in physics. To respect them, we have inverted, as we have already done in 3 dimensions. Now, let's give a summary of the present lecture. The differential formulation of physics, making use of point functions that are commonly field functions, commonly called field functions, needs a coordinate system in the space region where the field is defined. And this is needed because to every point we must associate an ordered set of numbers, its coordinates. If, instead of the point function, we use the global variables that are domain functions, we must consider not only points but also volumes, surfaces and lines. This invites us to introduce a cell complex in order to have at disposal also cells, that is volumes, with their faces, surfaces and their edges, lines. As a preliminary example, we have considered the heat conduction in a linear sequence of adjacent rooms. The fact of approximating the mean temperature of every room with the temperature in the centroid of each room suggests to consider these centroids as vertices of a second cell complex. A cell complex leads in a natural way to a classification of these 4 elements, that is, the cell, the faces, the edges and the vertices. In this way we obtain a classification diagram for space elements. Each space element can be endowed with inner orientation. There are 2 types of orientation. with orientation, sorry. There are two types of orientation, the inner or interior orientation and the outer or exterior orientation. The orientation of a space element can be applied to all elements of a cell complex. In this way we say that the whole cell complex is oriented. The cell complex that we have considered as primal will be oriented with an inner orientation, while the dual complex will be endowed with outer orientation. The inner orientation of the primal complex automatically induces an outer orientation to its dual. Hence, we are at the end of the third part, and we have here a statement of Poincaré. To sum up, the aim of mathematical physics is not only to facilitate for the physicist the numerical calculation of certain constant or the integration of certain differential equation. It is above all to reveal to him the hidden harmony of things, in making him see them in a new way. This is Henri Poincaré, The Value of Science. Look here, it is beautiful, this Greek person that is called the Bronze di Riace in Italian. Thank you very much.